చక్కగా ఉంటుంది సీట్ నేర్పిస్తాను मैं सोच रहा कहीं शिफ्ट हो जाए ये सोच रहा था बताओ
लगा देना अरे लगा देना कोई तो लगा देना
यार मैं तो चल चलती मेरा को घर जाना है
कॉल है आपकी
हाँ ठीक ही है वैसे देखना पड़ेगा
चल मैं सही करके तेरे को भेजता हूँ
So remember, in this course we are going to conduct two quiz in addition to the minus. Correct? So quiz minus will be from 12 to 18. Isn't it? 12 September to 18 September. Quiz 1 we will have on 20th October. Please note that 20th October is Sunday. I will notify the time. Quiz 1 will be on 20th October and quiz 2 will be on 10th November. So 14th is the last teaching day. Isn't it? So last quiz we will have on 10th November and the first quiz will be on 20th October. Both are Sunday. The quiz will be held in LX325. LX325, I will have to look at, but tentatively these are the days. Okay, so if you are planning to go out, timing is not fixed. Typically you can consider that you will have it between 10 to 12. If not something, if I am having on Sunday, then you will have it in the afternoon. But this will be on 20th October and 10th November. Quiz 1 will be on 20th October and quiz 2 will be on 10th November. Both are Sunday. Tentatively it will be held at lecture hall C25, which has 500 capacity, so that you can take your seat. Timing will be 2 hours, same as minor. It will be exactly same as minor. Okay? So I am informing you very in advance so that you can plan your holidays if you wanted to go out, whatever. Otherwise, last two rows will come different.
ये भी लिख के 2 घंटे किया, ये भी लिख के 2 घंटे किया। चलेगा?
Okay, so those who came late, there is the announcement. We will have quiz 1 on 20th October. That will be 1 week after your midterm break. So after your midterm break, we will have a quiz 20th October, first quiz, and the second quiz we will have it on 10th November. Okay. Last teaching day is 40th November. We will have it on 10th November, and both these dates are Sunday. Please note that both these dates are Sunday. Okay. So I will have to book the room. Typically, we usually conduct the quiz at LS325. Timing, which one you like, in the afternoon or in the morning? Evening नहीं. Sunday लाइव मेरा भी कुछ नहीं है. Morning नहीं. Afternoon करते 2 to 4. Sunday क्या है? 2 to 4. 10 to 12 I wanted to have a time on 4 whether I will be free in that time or not. I usually have a course, online course on Sunday. So I am not sure. But if I am free, then we can have it in morning, otherwise in the afternoon. Okay, 2 to 4. So 2 hours free, exactly same as mine. Sitting plan and everything will be, that will be conveyed to you in due course of time. LS325, there are 500 sitting places are there, so enough seats are there, isn't it? To accommodate everybody. Other than that, if you wanted to plan your holidays, you plan accordingly. Okay, there is no re-quiz. Please note that there is no re-quiz. If you miss more than one examination out of minor and 2 quizzes, you have missed. There is no re-quiz. Okay. So base 2 we are going to count, that means you have a choice of missing one. Alright? Okay? So please buy books before the examination. Okay? So in the last class we started looking at Laplace transform, isn't it? We said Laplace transform primarily because the model equations which we are going to have, these are usually differential equations, and if you apply the Laplace transform then you get algebraic equations, and solving algebraic equations is much more easier compared to solving differential equations, and that is the reason why we use Laplace transform in linear process. Okay, then we have seen the Laplace transform of some of the commonly used functions. Okay, again I wanted to repeat that we have not even started the proper process control. We are still at introduction itself. Okay, When we will start first order system, from there our usual process control will start. We are only building the concept, and that is why I am most of the time rushing through the material, because these are the basics which you have already done in other courses. Okay, some part is already done, and we are trying to connect these bits and pieces so that we can make a good story here. Okay, all right. Okay, so in the last class we have seen the Laplace transform of some of the commonly used functions. This first function we have seen, then we have seen the Laplace transform of derivative, we have seen the Laplace transform of integral function, isn't it? And after that we have also tabulated the Laplace transform of some of the commonly used functions. Why we are doing this? Because later on, whenever we are applying the Laplace transform, we are going to use this formula directly. We are not going to derive them again and again. In fact, you can see that there is some, some order is there in all these formulas. If you look at these formulas carefully, you can make out what will be the Laplace transform of some modified function. For instance, you can see that if you are having a function like e raised to the power minus at sine omega t, you already know that the Laplace transform of e raised to the power minus alpha t is what? 1 upon x plus alpha, isn't it? And for sine omega t, that is omega divided by x square plus omega square. So you can see that now both the things you have to combine. So whenever there is a s, that s will be added with a. So there is some logic is there if the modified function is there. Okay. Of course, you can derive all these formulas by using the definition of Laplace transform. The definition of Laplace transform is f of s is nothing but integral 0 to infinity f of t e raised to the power minus st d. Okay, that definition you can use and you can do that. Now let's look at the new things today. The first one is final value theorem. Final value theorem is extremely important in this course. I will give you a context why I am saying it is important. Remember, we have seen the controllers earlier. Let me go back. Okay. So here we are finding that whenever we are using a proportional controller, we typically get offset. Offset is not zero unless our controller gain is infinite. Isn't it? In a real life practice, having an infinite control gain is not practical because that may lead to instabilities, and therefore we will be using conservative value of the controller gain, and hence most of the time we will have offset. Offset is nothing but what? It's a steady state error at time t tends to infinity. It is nothing but the steady state error at time t tends to infinity. Now we have done all. So see, this steady state error at time t tends to infinity, we can directly obtain that. We can directly obtain that. You don't have to solve. You don't have to solve the response and find out what is the response of the system at time t tends to infinity. You don't have to do that. You can directly get that by using final value theorem. As the name suggests, the final value of the function you can directly get by applying the final value theorem. Okay. The caveat here is the final value theorem is not applicable for all the functions. It is applicable only for closed functions. So if you are having the functions those are periodic in nature, typically if you are having a sine wave as your function, then if you apply the final value theorem, you are not going to get the correct result. You are going to get the erroneous result. Okay. Final value theorem is applicable only for closed functions, not for periodic functions. Okay. Remember this. So let's go back again to final value theorem. What final value theorem says is, if I wanted to find out the value of this function f of t at t tends to infinity, so we are interested in finding out the final value of this function f of t when t is a very large value. I can directly get that from its Laplace transform. I don't need to find out how this function is varying with respect to time. I don't require. Remember, in this course I will have model equations and I can apply the Laplace transform. So definitely I know what is the Laplace transform of f of s. Most of the time I know Laplace transform of the function. Even without converting it into a time domain, I can find out the value of the function directly by using this theorem. What this theorem is saying, limit t tends to infinity, f of t is nothing but limit s tends to 0, s f of s. So if you know the Laplace transform of a function f of t, I can multiply that particular equation by s and then take a limit s tends to 0. That will directly give me the final value of the function f of t. I don't need to solve it in time domain. The advantage is I don't need to solve in time domain. That is the interesting thing. Sometimes the function f of t, if you apply the Laplace transform, you get a complicated equation. And if you wanted to revert back into a time domain, it is not that easy. It is not that easy. But you can still find out what will be the value of the function at t tends to infinity directly by putting s tends to 0 and multiplying the entire Laplace transform by s. Okay? Is it clear? Now this can be derived directly. You can see that this is the equation of Laplace transform of derivative. Laplace transform of derivative is given by what? S f of s minus f of 0. Isn't it? So this is the initial value. This is the value of the function at time t equals to 0. If you subtract that from s f of s, that is the Laplace transform of derivative. This we have already derived in the last class. This we have already derived. Okay. Now let us look at this left hand side. Left hand side is given as limit t tends to infinity f of t, isn't it? Correct? And we have to find out this right hand side. Now take the definition of Laplace transform of derivative. This is the function we have obtained. So Laplace transform of dft by dt, I can represent this in terms of the actual definition of Laplace transform, which is nothing but integral between 0 to infinity. This function as it is multiplied by e raised to the power minus st dt, and this limit we have taken s tends to 0 on both the sides. So if I take a limit s tends to 0 on both the sides, the same limit will be on the right hand side. Right hand side is this, isn't it? Which we can put as limit s tends to 0, s f of s minus f of s. Correct? So this is clear to everyone how we got this? We have just used this particular equation and taken the limit s tends to 0. क्या हो गया भाई? क्यों स्क्विड गेम खेल रहे हो यार? इधर आ जाओ, बाहर आ जाओ. क्या बात है? कुछ हमें भी बताओ, हम भी ऐसे गया थोड़ा. Your friends are also waiting. If there is anything interesting, is there anything interesting? अगर इंटरेस्टिंग नहीं तो ध्यान दो. ठीक है? Okay, all right. So this is the definition we have used directly here. Now limit s tends to 0 is there. I can take that limit inside this integral sign, isn't it? If I put s tends to 0 in this particular equation, what will happen to e raised to the power minus st? It will become 1. Isn't it? It will become 1. Exponential function tends to the power 0, that is 1. So we will have only dft by dt, and this dt will get cancelled out. So we will have only the integral between 0 to infinity dft. Isn't it? And what will be the integral of dft? F of t at infinity minus f of t at 0. That is what I want to get. Isn't it? So that is what we have written here. You can see this entire function is represented as dft, and the integral of this particular function will be f of t at t tends to infinity at f of 0. And right hand side will be again the same. Limit s tends to 0, s f of s minus f of 0. Now this f of 0 here and this f of 0 here on the left hand side, both are same. Isn't it? Both are same. So I can cut these two. Isn't it? So what I am getting? What is the remaining here? Limit t tends to infinity, f of t is given as limit s tends to 0, s f of s. So that is nothing but the equation which we are talking about here. Final line. Okay. Correct? Is it clear to everyone? Now let us look at the initial value theorem. Initial value theorem is similar to this. The only difference here it is t tends to 0 and here it will become s tends to infinity. You can derive the equation in a similar way. This is the definition of Laplace transform of derivative. Again put limit s tends to infinity. Isn't it? If I put s tends to infinity, what is I am going to get? This e raised to the power minus sc. If I put s equals to infinity here, this entire term becomes 0. So left hand side is 0. This left hand side is 0. Right hand side is what? S f of s minus f of 0 and s tends to infinity. Isn't it? This is what I am getting, and left hand side is 0. If I rearrange this, limit s tends to infinity, s f of s should be equal to f of 0. And what is f of 0? F of t at time t tends to 0. So we can prove both initial value theorem and final value theorem easily by using the Laplace transform, and its different forms of the Laplace transform for, by taking this particular Laplace transform of derivative, we can find out the initial value theorem and final value theorem. Okay, so far we have seen that why it is required, then model equation, then we again came back with concept of degree of freedom, then we have looked at Laplace transform, isn't it? All these dots we are trying to connect one by one, isn't it? And that is why these are covered initially, so that we can apply all these concepts together and solve our system easily. Okay, let's look at this particular problem which we have seen earlier. This is the same problem which we have seen. Remember, this is the same problem we have derived earlier. I will go back. Remember, this is the equation we have derived. We said this fi is not varying. In that case, only differential equation I am going to have with this v dt by dt is fi pi minus t plus lambda fst divided by rho cp. If I divide this entire equation by v, I get dt by dt plus alpha t is equal to 1 by tau pi plus kfst. This is the equation we have derived. Again, this equation we can represent in a deviation form. So we can subtract the equation at steady state and we can get the same equation in a deviation form like this. We can solve this equation by using the same standard solution of the linear differential equation. This is the standard linear differential equation. We can solve this and this is the solution. Isn't it? Now you can see that this particular equation is not easy to solve. It is slightly more difficult. But if we apply the Laplace transform, you will see that it is not that difficult to solve. It becomes easy. Okay. So that is what we are trying to appreciate in the current slide. Okay. Again, I will go back. So this is the same differential equation which we have obtained in a deviation form. Isn't it? It's a deviation form. That means what? This c dash is nothing but what? T minus cs. This pi dash is nothing but what? Pi minus tis. And similarly this fsc is nothing but fsc minus fscs. Okay. So all these variables are given in a deviation form. There is a reason why we have derived this equation in a deviation form. That will be clear to you. Now let's assume that in this particular problem, my temperature, initial temperature, whatever the temperature value it had, steady state value, it is increased by let's say 10 degrees. Isn't it? So what value I am having? Ti dash is what? 10. Isn't it? Whatever the steady state value it had earlier, I am increasing the value of this variable by 10 degrees. Isn't it? So Ti minus Tis is equal to 10. That means Ti dash is equal to 10. Okay. Again, for a simplicity, let us assume that the manipulated variable which is FSC, I am keeping the FSC same as the steady state value. I am not changing. I can change that also. There is no problem. But just to appreciate the concept, let's assume that FST is not being changed. FST is exactly same as its steady state value. So that means FSTS and FST both are same, and therefore FST dash is equal to 0. FST dash is equal to 0. Okay. I wanted to find out how this T dash is going to change with respect to time. Remember, in this course I wanted to understand how my control variable, which in this case is temperature, is going to vary with respect to time if there is a external disturbance. In this case, now the external disturbance is Pi. Since Pi is changing, with respect to change in Ti, how my control variable T is going to change with respect to its steady state value. Okay, that is what I am interested in. Typically, if I don't use a Laplace transform, I would have solved the linear differential equation which I had earlier. Isn't it? That linear differential equation I would have solved, and finally whatever the solution is obtained, that would have been the final solution. Isn't it? Now the same solution you can obtain directly by using Laplace transform. And that is the reason why we are looking at Laplace transform in this case. So in this case, let's say Ti dash is 10 and FST dash is 0. If I calculate the Laplace transform of both these inputs, what I am going to get? What will be the Laplace transform of Ti dash? It's a fixed value. Laplace transform of a constant is what? Constant divided by s. So Laplace transform of Ti dash in this case is going to be Ti dash s. Now it is a function of s. Currently this Ti dash and FST dash, these are given in a time domain. What their values are going to be in a s domain? In the s domain, this is going to become Ti dash s, and Ti dash s is going to be 10 divided by s, because Laplace transform of a constant is constant divided by s. Okay, so 10 divided by s. Similarly, Laplace transform of FST dash, it is going to be 0. It is going to be 0. Okay. Now apply the Laplace transform to this entire equation. What will be the Laplace transform of this derivative? S T dash s minus T dash 0. Isn't it? That is what is written. S T dash s minus T dash 0. Isn't it? What will be the Laplace transform of this? Alpha into T dash s. And that is equal to 1 by tau Pi dash s plus k FST dash s. Now you can replace this Pi dash s and FST dash s. So Pi dash s is what? 10 divided by s, and this is 0. So if I put that, and this T dash 0 is what? T dash 0 is the initial value of the T dash function at time t equals to 0. And at time t equals to 0, my actual temperature is exactly same as steady state value. So what will be T dash 0? 0. Now you can understand here that why this entire equation we have taken in a derivation form, because that helps me in solving. In this case, only the first order derivative is there. That is why only one initial condition is required. But remember, if you are having nth order derivative, you require n initial conditions. And all these n initial conditions become 0 if your equation is in a derivation form. I have written that earlier. I am not sure whether you remember that. So see, if you are having the nth order derivative, you have n initial conditions, 1, 2, 3, all the way to n. There are n initial conditions, and all these n initial conditions become 0 if you write your equation in a derivation form. And that is the reason in this course all our model equations we write in a derivation form. Okay, correct? Clear? Okay, so now this value is 0. Now you can rearrange. If you rearrange this entire equation, what you are going to get? T dash s comes out to be 10 divided by s tau, and in the bracket we are getting 1 upon s plus alpha. So whenever we have an equation like this, what we do? Typically, in order to solve the equation like this, we do a partial fraction. I don't know whether you remember or not. In a Laplace transform, when you wanted to invert it into a time domain, you use the method partial fractions. You write your equations in terms of partial fractions, and each of these partial fractions then you invert back into time domain. Okay. So in this case, you can see that this denominator is having order 2. See, s is here, and there is one more term, s plus alpha. So order is 2. So typical way of solving is you find out the roots of the denominator, and then you write your equation in terms of partial fraction of the roots. Okay. So in this case, you will have 1 upon s, that is one root, and another root is minus 1 upon s plus alpha, isn't it? And outside you are going to get 10 divided by tau alpha. You can rearrange this, you will get the same equation back. Okay, same equation back. Once I write down this equation in terms of partial fraction, now inverting this particular equation in time domain is easy. Remember, ultimately I wanted to know how my temperature is varying in time domain, not in s domain. Laplace transform I have used here only to simplify my analysis, there is no reason other than this, isn't it? Finally, I am interested in getting the value of this t dash in time domain, not in s domain. So I have to invert back this into a time domain. I can invert back this into a time domain directly. This 10 divided by tau alpha is a constant term that will come out, and 1 by s. What is the Laplace transform? Inverse Laplace transform of 1 by s? That will be 1. Laplace transform of 1 is 1 by s. So inverse Laplace transform of 1 by s will be 1. Isn't it? Similarly, inverse Laplace transform of 1 upon s plus alpha minus e raised to the power minus alpha t. Isn't it? So we have obtained this equation. This equation we have obtained. So you can see that the solution we have obtained very easily. In fact, the same solution you are going to get if you solve this differential equation. If you solve this differential equation and put all the values here, remember what is Ti? Ti dash is 10. Fs is 0. So e raised to the power alpha t into 10 and dt, and that integral between 0 to t. If you solve this, ultimately you will get the same equation. Same equation you are going to get. Okay. Clear to everyone? Is it clear to everyone? Where we are? So this is the equation we have obtained. Now this is a very simple equation, just to appreciate the concept, isn't it? Remember I said there are different dots we are trying to connect, isn't it? That's why we are doing these in bits and parts, and whenever that connection required to be established, we are trying to connect these, isn't it? So now, this is for a very simple case. But remember I said in this course you will have complicated equations. You will be getting complicated equations, and you have to invert that into time domain, isn't it? Now if you look at this equation, this particular equation, so what this particular equation is giving you? This particular equation is control variable is there in the s domain, and that control variable is represented in the form of polynomials in s. So here you can see that there is only 10 in the numerator and st into s plus alpha in the denominator, isn't it? There is no s term in the numerator, but you will see in this course that in some cases, and in some specialized cases, you also get s term in the numerator. So that is why I am using this in a generalized way. I am saying that the control variable will be represented as the ratio of two polynomials in S. Okay, and that is what is represented here. So usually your control variable will be represented by ratio of two polynomials, Qs and P of S. So Qs is nothing but all the terms which are there in the numerator, and Ps is all the terms which are there in the denominator. One more important point to note down, and which is commonly asked question in the interview. Typically, this Qs will have lower order polynomial compared to P of S. I am not giving you the reason for that now, isn't it? But for all practical purposes, I am saying Q of S will be a lower order polynomial compared to P of S. Okay. If you wanted to select any mathematical function that you can select, there is no problem. But in the practical cases, you are not going to have that type of equation. That is what I am saying. There is a reason for that. If your Q of S is a higher order polynomial than P of S, typically what it means is you are trying to get the future values in the current time, which is not possible. We will prove this fact later. As we go ahead, we will prove this. But just to give you a context here, Q of S is going to be a lower order polynomial compared to P of S for all practical purposes. Mathematically, you can have Q of S higher order polynomial than P of S, but in practical purposes, you are not going to get that. Okay, that is what I am trying to say. Is it clear to everyone? So this is the control variable which is represented as a ratio of two polynomials Qs and P of S, isn't it? Ultimately, I am interested in finding this xt. Ultimately, I am interested in finding how my control variable x is varying with respect to time t, not in terms of s, isn't it? So that means what? This entire equation I have to invert back into time domain. Isn't it? I have to take an inverse Laplace transform of this entire equation. Isn't it? In the last slide we have discussed, in such cases what we do? We write this entire equation in terms of partial fractions. Partial fractions of what? Partial fractions in terms of roots of denominator. In this case, denominator is P of S. We can find out how many roots are possible for P of S. Let's say there is a nth order polynomial in the denominator and it has roots R1, R2, R3 all the way to Rn. Let's say there are n roots are there. I can write down the partial fractions in terms of all these roots as C1 divided by R1s plus C2 divided by R2s, and that summation goes all the way to Cn divided by Rn. So we have converted this equation in terms of partial fractions where R1s, R2s, Rns, these are the roots of polynomial P of S, and C1, C2, C3, Cn, all these are the constants, and these constants we have to find. अभी भी नहीं खत्म हुआ तुम्हारा स्पीड गेम्स, इससे बता दो यार, सब लोग को मजा आएगा। कुछ मजा नहीं आ रहा है कोर्स में? ठीक है, बताओ, कुछ बताओगे तभी तो आगे बढ़ेंगे, बता ही नहीं रहे हो। देखो इन लाइव सोची जितने भी सक्सेसफुल लोगों को देखोगे ना, इट इज नॉट बिकॉज ऑफ इंटेलिजेंस दे आर सक्सेसफुल, इट इज बिकॉज ऑफ डेडिकेशन दे आर सक्सेसफुल। ओके, इस कोर्स में कुछ सीखो या ना सीखो, कम से कम डेडिकेशन जरूर सीखिए। ठीक है, चलो लेट्स गो। So now we have written this equation in terms of different partial fractions. These are the different partial fractions which we have written here. Now we can invert this entire equation in a time domain easily. How? So what will be the inverse of this particular term? C1 into Laplace transform of 1 by R1s, isn't it? Correct? So that is what we have written. Xt will be given as Laplace inverse of C1 R1s plus the inverse Laplace transform of C2 by R2s, and that summation goes all the way to nth order term. Okay. So this is the general solution procedure when you wanted to invert back the given polynomial which is there in the S domain. Okay. Now there are multiple cases are there. Okay. The first important case here is, let's say all these roots R1, R2, R3, these are the roots of polynomial PS. Let's say all these roots are real and distinct. There are three cases possible. When all the roots are real and distinct, when the roots are imaginary, And third possibility is when the roots are multiple roots. We are going to look at each of the possibilities little bit in more detail. Okay. So let's look at the first case when all these roots are real and distinct. Real and distinct. And you will see that why these cases are important, because a important conclusion we are going to draw from this. Okay, very important conclusion, and that is related to the stability. Okay, so it is not just for sake of solving we are doing it. Probably many of you are already knowing how to solve it. Okay, the important message which I wanted to convey here is how these solutions are going to impact your stability of your control system. That is what we are going to look at in more detail as we go ahead. So let's look at the first case. The first case is the roots of the polynomial are real and distinct. Let's take an example. X of s is given as qs by pl, where the equation given here is numerator qs is given as s square minus s minus 6 divided by the denominator g of s is s cube minus 2s square minus s plus 2. Okay. Now in this case, remember how we separate the partial fractions based on the roots of the denominator. Denominator in this case is p of s. P of s is having the order 3. So how many roots are possible? 3 roots are possible. Isn't it? 3 roots are possible. Because the degree of s in the denominator is 3. Correct? So this denominator we can represent in the form of different roots. So in this case there are 3 roots possible. P1 equals to 1, P2 equals to minus 1 and P3 equals to 2. These are the 3 roots. And with respect to these 3 roots, the factors I am going to have with respect to this denominator will be s minus 1, s plus 1 and s minus 2. These are the 3 factors. If you multiply these 3 factors, ultimately what you are going to get is the same denominator. Okay. So my equation is this now. This equation I have represented in the form of factors of this denominator. So you can see that s square minus s minus 6 divided by s minus 1, s plus 1 and s minus 2. Now I am separating this equation in terms of different partial fractions. So c1 divided by s minus 1, that is the first partial fraction. c2 divided by s plus 1 is the second partial fraction. And the last one is c3 divided by s minus 2. These are the 3 partial fractions we have written. I can invert this equation easily now. Isn't it? What will be the inverse Laplace transform of this equation? Inverse Laplace transform of this first term will be c1 and s minus 1 is there. S minus 1 inverse Laplace transform e raised to the power t. Similarly, the inverse Laplace transform of this term will be c2 e raised to the power minus t, because there is a minus 1 plus 1 here, isn't it? And the last term I am going to have c3 e raised to the power 2t. Now only thing remaining in this particular equation is to find out the values c1, c2 and c3. Isn't it? How we find out c1, c2, c3? This is the equation, this is the original equation. I can multiply this original equation by s minus 1. If I multiply this original equation by s minus 1, this s minus 1 will get eliminated here. This s minus 1 will be eliminated here. And s minus 1 will come here in the numerator. S minus 1 will come here in the numerator. So that is what we have written. See. And this s minus 1 will get cancelled out. Once we have obtained this, then we have to put s equals to 1. Put s equals to 1. First multiply this factors to the entire equation and then put s equals to 1. If you put that, what you are going to get? See, this entire term is going to become 0. This entire term is going to become 0. And you will get right hand side only c1. So right hand side only c1 is there. If you put s equals to 1, this factor will get cancelled out. If you put s equals to 1, find out what is the value of c1 you are getting. So value of c1 comes out to be 3 in this. Similarly, in order to find out c2, what you have to do now? You have to multiply this entire equation by s plus 1 and then put s equals to minus 1. Okay. With that you are going to get c2, which comes out to be minus 2 by 3. And similarly, for the third case, you have to again multiply the entire equation by s minus 2 and then put s equals to 2 in the entire equation. You will be getting C3. So C3 comes out to be minus 4 by 3. Now I can put C1, C2, C3 in the original inverted equation, isn't it? This C1, C2, C3 we can back substitute in this equation, and that is the solution of your equation, isn't it? So if you back substitute, what we are getting? We are getting this. Xt is given as 3 into e raised to the power t minus 2 by 3 e raised to the power minus t minus 4 by 3 e raised to the power 2t. This is the solution. Now what is important point to note down in this case? Whenever I have real and distinct root, my response is always exponential. This is what the important conclusion is. Whenever I have roots which are real and distinct, my response is exponential. Okay. Now let's look at another case. Another case is where the roots are now imaginary. Remember in the previous case we have taken the roots which are real and distinct. Now let us assume that the roots are imaginary. So for that again we have taken another example. X of s is given as qs by ps, which is given as s plus 1 divided by s square minus 2s plus 5. Here if you look at the denominator p of s, the roots of the denominator are 1 plus 2j and p2 is given as 1 minus 2j. So you can see that both the roots are imaginary. One more thing to note down is imaginary roots always occurs in conjugate pair. Okay. So these are the two roots which are imaginary. I can again put these roots in terms of the factor. So what will be the factor in this case? S minus 1 plus 2j, that will be one factor. Another factor will be s minus 1 minus 2j, that will be another factor. So you can see that this original equation we have represented in terms of two factors. S minus 1 plus 2j and s minus 1 minus 2j, and C1 and C2 we have taken in order to separate the partial factors. Is it clear to everyone? Now what will be the inverse Laplace transform of this? Inverse Laplace transform of this will be C1 e raised to the power 1 plus 2 iota into t. Isn't it? 1 plus 2j and outside t I will have. This second term will be inverted back to time domain, and that will be given as C2 e raised to the power 1 minus 2j into t. Here j is the iota, isn't it? Now this is what the equation we have obtained. We have to find out C1 and C2. How we find out C1 and C2? The same procedure which we have followed earlier. What was the procedure? I can multiply this entire equation by s minus 1 plus 2j and then put s equals to 1 plus 2j. With that, I can find out C1. You can see that in this case, if I do that, the C1 comes out to be 1 minus iota divided by 2. Similarly, in order to find out C2, what I have to do? I can multiply this entire equation by s minus 1 minus 2j and then put s equals to 1 plus 2j. And with that, we can again find out C2. C2 comes out to be 1 plus iota divided by 2. Then we can put this C1 and C2 back substitute in the original equation. This is the original equation we have obtained in time domain. I can put this C1 and C2 directly obtained here in this equation and see what we get. So once we put this C1 and C2 in the equation, what we get is this. Xt is 1 minus iota divided by 2 e raised to the power 1 plus 2 iota t plus 1 plus j divided by 2 e raised to the power 1 minus 2j. Okay. Now both the exponential term has e raised to the power t, isn't it? This I can write down as e raised to the power t and e raised to the power 2j. And e raised to the power t I can take it out, and this divided by 2 also I can take it out. So that is what is done here. E raised to the power t divided by 2 is taken common. Whatever remaining here is 1 minus iota e raised to the power 2j plus 1 plus iota into e raised to the power minus 2j. Now again, this exponential term I can write down in terms of sine and cos. So e raised to the power 2j t is given as cos 2t plus j sin 2t. Similarly, e raised to the power minus 2j t is written as cos 2t minus j sin 2t. If I put these two terms here, ultimately what we get here is e raised to the power t cos 2t plus sin 2t. Where? Here? Cos 2t. नहीं correct है यार. Everything is correct. I have checked. Some mistakes are there in your printed version. Okay, please check carefully. I have corrected this here. Okay, some small minor mistakes are there which we are correcting as we go. Okay, so these notes are made last year, so there could be some errors in between. So whenever I point out some error, I correct it. So once we have obtained this particular equation, again this can be further simplified, isn't it? So this term can be represented as under root 2 sin 2t plus phi. This is the property we have used. A1 cos b plus a2 sin b is written as a3 sin b plus phi, where phi is the phase angle, isn't it? How we get the phase angle? Tan inverse of a1 divided by a2, isn't it? And what will be this a3? A3 is nothing but under root a1 square plus a2 square. Okay, so with that we can obtain this equation xt is given as e raised to the power t under root 2 sin 2t plus 45. Here phi is 45. Okay, now the important point to note down here is, unlike the previous case where my response was exponential, when my roots are real and distinct, my response is exponential. But when my roots are imaginary, my response is what? Periodic. This equation is periodic. I am getting a sine wave here. So my response is periodic. Okay. So whenever I have the imaginary roots that lead to a periodic term, so you will see that your response will be fluctuating like this, sine wave or cos wave, depending on what you are getting. Okay. All right. Another important thing to note down is your response is lagging behind here. Stage lag is there, phi. Okay. Again, one more thing to note down here is the complex roots always occur in conjugate pair. Okay. All right. One more special case is there that we will see in the next class. Okay. So there is one more case where we are having a multiple roots that we will see in the next class. And these are very, very interesting cases. Why? Because later on in the stability you will see the location of the roots actually decides the stability of your control system. And that is why with roots we are finding out that. Okay, please stop here. I will check.
छुट्टी हो गई भाई तुम लोगों की तो
देरी नहीं हुई
हो गया क्या हुआ ड्रेस चेंज कर निकल जा रहा हेलो क्या चल रहा है चेस खेल रहे थे
वो क्या बोला?
चार